17 tons of titanium and steel, engineered to reach the deepest points on the planet, descending through 3,000 feet of pitch-black ocean in the Gulf of Mexico. And then it stops, not because it hit the seafloor, because it hit a lake. A lake sitting on the ocean floor, with its own shoreline, its own slow-rolling waves, and what looks like white sandy beaches. And the submarine is floating on its surface like a cork. The pilot releases a single 100-pound steel weight, an action that in normal seawater would produce a slow, gentle rise. Instead, the 17-ton vehicle rockets 22 meters upward in seconds. The liquid below looks exactly like water through the viewport. It ripples like water, but whatever it actually is, it just rejected a submarine. And anything alive that swims through that surface doesn't bounce back out. It dies, instantly, and its body will still be sitting on the bottom of that lake decades from now, perfectly intact, looking like it died this morning. These are deep-sea brine pools, and they are among the most hostile environments on Earth. 165 million years ago, the Gulf of Mexico wasn't an ocean. It was a shallow, landlocked sea baking under an arid Jurassic sun. It flooded when rising waters breached its rim. It evaporated when they retreated. Over and over for millions of years, each cycle crystallizing another layer of pure salt onto the basin floor. By the time the process ended, there was a salt deposit beneath what would become the Gulf, reaching thicknesses of up to 5 miles. The height of Everest, in solid mineral. When the global ocean eventually reconnected and flooded the basin permanently, the salt was buried under millions of years of sediment, mud, sand, the slow rain of dead organisms drifting to the bottom. Under that immense weight, the salt began to move. Over geological time, salt under pressure doesn't behave like rock. It behaves like an extremely viscous fluid, deforming and migrating upward through faults in the overlying strata, forming massive subterranean columns called salt domes. Where those domes breach the seafloor, seawater dissolves the exposed mineral into a superconcentrated brine loaded with sodium, chloride, methane, and hydrogen sulfide from surrounding hydrocarbon reservoirs. And because that brine is profoundly heavier than normal seawater, it sinks. It cascades downslope and pools in every depression it can find, forming bodies of liquid so dense they refuse to mix with the ocean above. The boundary between the two fluids is so sharp it creates a visible surface, complete with shorelines, beaches, and in some locations, underwater waterfalls of shimmering fluid spilling over the crater's edges. The Orca Basin, off the Louisiana coast, covers an area roughly the size of Denver and holds a column of toxic brine 200 meters deep, taller than a 60-story skyscraper. The Jacuzzi of Despair, by contrast, is barely 100 feet across, a compact circular pool heated by geothermal energy to 19 degrees Celsius, in water that otherwise hovers just above freezing. Similar formations have been found in the Mediterranean Sea and the Red Sea, but the Gulf of Mexico, sitting atop that ancient salt, holds some of the most studied and most visually striking examples on Earth, and from a distance, every one of them looks beautiful. When the high-intensity lights of a submersible sweep across a brine pool for the first time, the scene is disorienting. After hours of navigating featureless gray mud, the deep ocean floor is one of the most barren landscapes on the planet. The vehicle arrives at what looks like a pristine coastal lagoon compressed into the abyss. A flat, milky surface stretches out, shimmering and reflecting the vehicle's lights exactly like a pond on dry land. The shoreline is ringed with terraced mineral walls, bright white crystals of barite that look indistinguishable from beach sand. A hazy, turbid fog hovers just above certain pools, making them look like something out of a storybook. Eric Cordes, the biologist from Temple University who helped discover the Jacuzzi of Despair, described the experience. You go down into the bottom of the ocean, and you are looking at a lake or a river flowing. It feels like you are not on this world. And the edges are teeming with life. Massive colonies of deep-sea mussels packed at densities exceeding 2,000 individuals per square meter. Roughly the floor of a shower stall, covered in 2,000 hard-shelled clams stacked on top of one another. Dense clusters of tube worms rise from the mud. Schools of pale shrimp hover just above the surface. Everything about the scene broadcasts abundance, safety, a biological oasis. Which is a lie. Every organism crowding that shoreline is exploiting the pool's toxicity, not its hospitality. The mussels and tube worms don't consume organic matter. They harbor symbiotic bacteria in their gills that convert the methane and hydrogen sulfide leaking from the brine into metabolic energy. They're fueled by poison. The white sand isn't sand at all. It's a chemical precipitate that forms when barium-rich brine collides with sulfate-rich seawater. And the biological density isn't evidence that the water is safe. It's evidence that the water is so toxic it generates enough chemical energy to sustain thousands of organisms per square meter without a single photon of sunlight. The animals that have adapted to this environment, the specialized shrimp, the deep-sea eels, know precisely where the lethal boundary is. They crowd the edges, never crossing. Everything that does cross does not come back. And the brine gives no warning of how different it is. Standard seawater has a density of about 1.04 grams per cubic centimeter. The fluid inside a Gulf of Mexico brine pool ranges from 1.15 to 1.24. That gap sounds modest, until you watch what it does to vehicles specifically engineered to operate at the bottom of the ocean. That density gap is why a submarine built to reach the deepest points on the planet couldn't penetrate the surface. The halocline, the razor-thin boundary where seawater meets brine, held off the DSV Alvin in the Orca Basin as completely as a physical wall. When the ROV Hercules tried a different approach at another pool, engaging its vertical thrusters at maximum downward power to force cameras below the brine surface, the vehicle shuddered and strained against the interface. The moment the pilot cut the thrusters, the ROV popped straight back out, like releasing a beach ball underwater. To retrieve even a small sample, the Hercules team had to mount a mechanical sampling bottle on a long arm beneath the vehicle and drive the ROV downward with everything it had, just to push the bottle past the boundary. Through the cameras, the fluid below looked identical to the seawater above. Nothing in its appearance suggested it could repel thousands of pounds of steel. But the buoyancy is a curiosity. What the brine does to something made of tissue rather than titanium, to anything actually alive, is what makes these pools the most lethal environment in the ocean. If you want to catch the next one of these, the subscribe button is right below. Every marine organism maintains a delicate internal balance. The salinity inside its cells is roughly calibrated to match the ocean around it, about 35 parts per thousand. That equilibrium is what keeps water flowing in and out of tissues at a manageable rate, keeping cells hydrated, functional, alive. It's the invisible architecture holding every marine organism together. The fluid inside a brine pool is not 35 parts per thousand. In the Gulf of Mexico, it ranges from 150 to over 300. In certain Mediterranean pools, it exceeds 470, more than 13 times the concentration of normal seawater, substantially saltier than the Dead Sea. And the transition between the two environments isn't gradual. It occurs across a boundary sometimes only millimeters thick. The moment a fish, an eel, or a crab crosses that boundary, every cell membrane in its body becomes a one-way valve. Water inside the animal's tissues is violently dragged outward, through gills, through eyes, through every exposed membrane, pulled across cellular walls by the overwhelming osmotic gradient in a futile attempt to dilute the brine. The organism is being desiccated from the inside out while fully submerged in liquid. And the brine isn't just salty. It contains zero dissolved oxygen, not low oxygen, absolute zero, and it is saturated with hydrogen sulfide, the same gas responsible for the smell of rotten eggs, but at concentrations in some pools reaching 6 million times higher than normal seawater. Hydrogen sulfide doesn't simply displace oxygen. It crosses biological membranes with ease, enters the bloodstream, and locks onto the iron center of the enzyme responsible for cellular respiration, cytochrome C oxidase, and shuts it down completely. The mechanism is functionally identical to cyanide poisoning. Even if the animal had oxygen in its blood, its cells could no longer use it. The combined effect is nearly instantaneous. Within seconds of breaching the halocline, the animal's mucous membranes are under assault from the salinity. Its nervous system is flooding with hydrogen sulfide, and motor control is collapsing. The body seizes into an opistotonic spasm, every muscle firing at once, the spine arching rigid, the animal contorting into shapes it could never produce voluntarily. If it can't thrash its way backward through the density barrier in those first seconds, it sinks into the heavy fluid and does not come back up. In 2017, BBC cameras captured this exact sequence in real time. A cutthroat eel, hunting the dense biological activity along a brine pool's shoreline in the Gulf of Mexico, swam directly through the halocline. The footage shows the eel entering the milky fluid and immediately convulsing, its body twisting and nodding as osmotic shock and hydrogen sulfide overwhelmed its nervous system. This particular eel managed, barely, to thrash itself backward into the oxygenated water. But what made the footage genuinely unnerving wasn't the eel that nearly died. It was the second eel, visible in the same frame, hovering calmly just inches above the lethal surface, entirely indifferent to the first eel's agonized convulsions. The margin between agony and indifference was measured in millimeters, and in certain pools, the lethality goes further still. In the Mediterranean, brine pools formed by the near total evaporation of the sea 5 million years ago contain not sodium chloride, but magnesium chloride, dissolved from a rare mineral called bischofite. In pools like Lake Creos, 3,500 meters beneath the surface, the magnesium concentration is so extreme that the dissolved ions physically disrupt the hydrogen bonds between water molecules, a threshold scientists call chaotropicity. Proteins denature, cell membranes dissolve, and enzymatic function ceases entirely. The fluid has become so chemically crowded that the water itself stops functioning as a biological solvent and instead operates as an agent of molecular disassembly. Tissue entering this brine isn't just killed, it is structurally taken apart. And then the pool does something that contradicts every rule of oceanic decay. In normal seawater, a dead organism disappears within days. Scavengers arrive first, then bacteria break down what remains. Inside a brine pool, there are no scavengers, and there are no bacteria. The salt concentration and the total absence of oxygen make the pool's interior as sterile as an autoclave. Nothing that enters survives long enough to feed. When researchers explored a pool cataloged as Green Canyon 246 in the Gulf of Mexico, they found so many perfectly intact crab carcasses lining the basin that the scientific community gave it a name, Dead Crab Lake. One ROV camera captured a deep-sea isopod that had simply tumbled in head first, its body frozen upright, half protruding from the brine surface, perfectly preserved like a specimen pinned in a display case. At the Jacuzzi of Despair, a robotic arm retrieved a crab that had been sitting in the brine for an estimated 8 years. The acidic fluid had leached the calcium from its exoskeleton, leaving the shell soft and rubbery to the touch. But the internal tissue, every organ, was perfectly intact. The pool had killed the crab in seconds, and then spent 8 years embalming it. And then there is what the deep ocean has learned to do with all of this. In 2020, researchers in the Gulf of Aqaba discovered a massive brine pool roughly 2.5 acres across, sitting at a depth of 1,700 meters. When the ROV surveyed the perimeter, its cameras captured something the team hadn't anticipated. Eels and shrimp positioned at the exact geometric edge of the halocline, hovering with surgical precision millimeters above the lethal surface. They weren't feeding on the mussel beds, they were hunting. When a scavenging fish, drawn by the dense biological activity on the pool's rim, accidentally drifted past the boundary, it was stunned in seconds, osmotic shock and hydrogen sulfide collapsing its motor control before it could react. As the paralyzed prey drifted helplessly back toward the surface of the brine, the waiting predators darted in, seized it, and pulled it into the oxygenated water to consume. These animals treat the halocline the way a spider treats its web. They don't do the killing themselves. They let the chemistry handle it and collect the results. A geological feature 165 million years in the making, weaponized by the organisms that have learned to survive alongside it. Only one vertebrate has ever figured out how to cross the boundary and survive. The deep-sea hagfish doesn't fight the salinity gradient. Its cells physically alter their own internal concentration to match whatever fluid surrounds them, equalizing with the brine rather than being destroyed by it. It swims into the graveyard, feeds on the pickled dead, and swims back out. The mineral wealth resting inside these pools is extraordinary. Beneath the Atlantis too deep in the Red Sea, where the brine temperature reaches 68 degrees Celsius, hot enough to cause third-degree burns in 2 seconds, sits an estimated 89 million tons of metalliferous ore, including 47 tons of gold. Mining consortiums have studied the deposit for decades, but extraction would require dredging through a lake of near-boiling hypersaline acid saturated with heavy metals, and breaching the halocline at industrial scale would release cubic kilometers of anoxic, metal-laden brine into the oxygenated Red Sea, devastating every living system it reached. So the pools sit, undisturbed, killing everything that enters and perfectly preserving the evidence, including, in their deepest sediment layers, something scientists never expected to find intact. An unbroken climate record stretching back more than 1,000 years. Because the toxic water kills every burrowing organism that might churn the seafloor mud, the sediment accumulates in perfect, undisturbed chronological order. Flash floods, rainfall cycles, ancient tsunamis striking the Arabian coast, all archived in thin ribbons of mud, kept pristine by the very chemistry that makes the water lethal. As Sam Purkis, the marine geoscientist who discovered the pools in the Gulf of Aqaba, put it, any sedimentary layers that settle to the bed of the brine pool remain exquisitely intact. The most hostile water on Earth is also its most perfect archive. The same chemistry that kills everything it touches is the only reason the record survives.